Yes, ma'am. We are live on YouTube as well as on Zoom. Good evening, participants. Welcome to the live session of the course, Introduction to Multi-Agent Systems. Our instructor, Professor Twinkle Tripathy ma'am, is here with us, along with our teaching assistants, Ms. Aditi and Mr. Pradeep. If you have any doubts, please feel free to ask, ma'am. Over to you, ma'am.
Thank you for the introduction. So, as he mentioned, if there are any questions, I'll be happy to answer them.
As of now, only one student joined, ma'am. That who? Let us ask that who. Do you have any question?
So, I see that he has asked some questions in the Google Sheet.
Yeah, maybe you can start with that one, ma'am.
Yes. Am I audible?
Yes, ma'am, you are audible.
Okay. So, this Dat Wu has asked a few specific questions pertaining to the applications of multi-agent systems. Okay. When combining formation control with consensus, how can we ensure not only velocity consensus, but also position and orientation? How is this principle typically applied in real systems such as UAV light shows? Okay. So the question has to be a bit more specific in the sense, given that you are here in that way, so I'd like to ask if there's any specific model of the agents that you're interested in. For example, in the beginning of the course, we discussed linear system, like linear models, single integrators, or double integrators, or unicycle. So the solution that we provide would actually depend on the model that we have. So far what we have covered in the course pertains to, can be applied directly to single and double integrator systems. However, you have mentioned here orientation consensus. So orientation generally is defined for systems which have a heading angle, meaning they have a unicycle like model. So I'm assuming this is what you have in mind. So unicycle or design of distributed algorithms for unicycle systems is not something that we have covered yet in the course. That will be covered in the next week. And the problem that you're talking about, velocity consensus, position consensus and orientation consensus. Again, there are many works which have addressed these kind of problems, and we plan to discuss some algorithm exactly to achieve this. So this question will be answered in the 11th week of the course. So I'll postpone this discussion to that point. Okay, the next question is regarding the mathematical foundation. Do I need to invest significant time in studying graph theory more deeply? Okay. And which core concepts are the most essential for MAS research? Okay. Now, in general, no, you do not need to focus on graph theory more deeply unless you're interested in a very specific problem in multi-agent systems which requires those notions. For example, if you're working on applications like structural controllability, you might need some notions which are generally not covered in multi-agent systems but are borrowed from graph theory. So there it becomes important to look at a little bit of graph theory. And but in general, no, whatever we have covered in the course so far is sufficient and can be treated as the foundation to build or develop distributed algorithms. Which core concepts are the most essential? So if you're looking at linear systems, it is some basic understanding of Perron-Frobenius is very important, because Perron-Frobenius theorem is actually the key to understanding how we can design various kinds of graphs and networks such that if you want to achieve consensus, we can actually ensure that using a suitable design of either the network or a suitable design of the distributed control law. And similar to that, when we'll be looking at in the 11th week, we'll look at dynamical systems and how would one design distributed control for a non-linear system like a unicycle. So in those cases, people use tools like Lyapunov theory, for example, to design distributed algorithms. Again, we'll look at an example of this in the 11th week. Okay, then I'm particularly interested in, cluster consensus and matrix weighted graphs. Okay. In practice, when we cannot arbitrarily design the network architecture, how feasible is cluster consensus? What advantages do matrix weighted graphs bring compared to scalar weights? And could you recommend some references or lecture notes for self-study? So this is a very specific question. Cluster consensus, yes, is a very active area of research, and there are two bodies of research. Like, for example, either we consider that the network which we are looking at, it itself has various clusters of nodes which form clusters for whichever reason, but it is predefined. Perhaps the reason is that these clusters are very strongly connected, and we can clearly see different communities, each community being a cluster. So, in one class of problems, people try to achieve consensus or develop again Laplacian based rules to achieve consensus in these cases, such that the consensus occurs between the agents within each clusters. So, cluster consensus, this is one way to do it. The second way would be, suppose now, in general, we want to achieve consensus arbitrarily. Then how would we design algorithms? Because in reality, we see that interconnections between people keep changing with time. Like there is a possibility. Perhaps the people who we interacted with before, as we keep on making more and more friends, interact with more friends, perhaps our circle also changes. Based on that, the cluster that we interact with in the beginning might not remain the cluster that we stick to for the rest of, whatever be the time that we are looking at. In those cases, cluster consensus or consensus could also be achieved where eventually echo chambers or clusters of opinions get formed where people start talking to each other a lot and then form a cluster where all of them achieve consensus. So that becomes yet another class of problem. So there are actually works which which deal with the development of distributed algorithms which can lead to cluster consensus. It is very feasible. We do not need to change the network architecture. What advantages do matrix weighted graphs bring compared to scalar weights? So we will look at the problem of opinion dynamics in the 12th week. So we will discuss these topics in more details then. Again, we will also do a live session for the last 4 weeks as well. So we can discuss these problems in more details then. So moving on, beyond convergence and stability, MAS control must also guarantee safety, such as collision avoidance. How can control barrier functions and safety constraints be incorporated into multi-agent systems? So again, in the 11th week, we'll look at how we can actually use Lyapunov functions to design distributed algorithms. And barrier Lyapunov functions or control barrier functions are actually very useful because, as you have rightly said, they can be used to ensure collision avoidance. So, although it is not a part of the lectures, but what we'll do is we'll add it as an assignment question and we'll provide solution to this question so that we can discuss it in more details. But again, this pertains to the 11th week. We'll be discussing it in a bit more details later on. When trading off between performance and safety, which approach does the research community usually prioritize? So this question has to be made a bit more precise. Meaning, what is the performance metric that we are looking at, and how is that performance metric actually affecting the safety of the system? So perhaps the question can be formalized a bit more. With a background in MPC, I'd like to ask, in distributed MPC, is it possible to maintain the original optimal control structure and only modify the cost or constraints? Okay, is it possible to maintain the original optimal control structure and only modify the cost to reflect neighbor interactions? What are the biggest challenges when scaling up or dealing with communication delays? And what strategies are commonly used to reduce complexity? Again, we can discuss this problem in the last week in more details. After finishing this course, what kind of practical example would you recommend I start with to implement a complete MAS pipeline? If my goal is to publish a paper within 1 year, what level of contribution? Okay, so these questions are not really pertaining to the first 4 weeks in the course, but nonetheless, I'll try to provide an answer. If my goal is to, what level of contribution would be suitable? So the idea is that it is very, very important to understand well what has been done in the literature, because only if we understand what has already been done, then we can figure out what are the limitations or lacunae in the existing literature. So it is very important to figure out a good problem to solve, and that only comes with a very good literature review. So you should start with that, and thereafter this course will introduce all the basic tools that is needed to get started. Solved consensus formation. So again, you can look at the lecture notes by Professor Francisco Bullo. He has introduced many of the basic topics that are needed to build a decent foundation in multi-agent systems. Which frontier topics in MAS would be the most promising to invest in? Okay. Now, learning-based things is a key focus in today's times, because learning seems to be giving a lot of promising results. So, as control engineers, we are trying to achieve guarantees. In a distributed setup, also we can use learning, and how can we get guarantees of convergence in those setups? So that is a very good problem to look at, and you can focus on that. So that you have asked a bunch of questions, but some of these questions will get clarified in the 11th week of the lecture, and perhaps when we do a live session for that, we can discuss these questions in more details. Is there any other question that you'd like to add here? Okay, what is the role of convergence to mean different from... Okay. What is the role of convergence to the mean? Again, this question has to be specified a bit more. Such a lot in your lecture. So can you specify which topic? Convergence to the mean. Okay, I'm guessing you mean the average of initial conditions. Okay, actually, in that case, this would be a very good question. So the question is, in which cases can we actually, in general, what happens is when we use a distributed averaging algorithm or the Laplacian flows, in both of the cases, the natural behavior of the system is to move towards some weighted average of the initial conditions. When the graph is undirected, then it converges to the mean of the initial conditions, or the average of the initial conditions. So the question is, can we somehow design distributed algorithms such that instead of converging to the average of the initial conditions, we now converge to some other value? Yes, it is very much possible to do that. And how would we do it? So There are again numerous papers on it, and you can refer to some of my papers, recent papers where we have talked about it. But I'll try to give a key idea of how this can be designed. Okay, so let's look at it. Now, when we're looking at a row stochastic matrix pertaining to the adjacency, in that case, the eigenvalue 1 generally has the eigenvector 1n associated with it, which often drives the convergence in the case of undirected networks. So because of this formulation, we get the average as the final consensus value. But now suppose we want to deviate from this and converge at a different value. Then what do we need to do? We need to change the eigenvector associated with the eigenvalue 1. That is the key idea. Meaning, we need to change the adjacency matrix in such a way that again it is a semi-convergent matrix, but the corresponding eigenvector is not 1n. Hence, we do not get convergence to the average or the mean value. So I hope this answers the question. I have read some explanations where I see people often mention mean convergence to achieve some condition about variance. Can you explain this for me? So the idea is that I would need a bit more context, so please feel free to you can mail us the particular reference that you're looking at, and in the next live session we can, or via mail, we can discuss it in more details. I'm often using clustering. Can you explain why it helps for clustering? So that who please share the particular references that you're interested in, and I can answer it better there. But we must remember the key idea is whenever we are looking at a semi-convergent matrix, where the overall system converges depends on the corresponding eigenvector. So if we can figure out a way to design the eigenvector suitably, then we are actually controlling where the consensus value goes to. Okay. There was one question before this. Can you tell us about any project ideas or research papers for this course? Well, yes, the last week of the course will deal with applications of multi-agent systems for real-world systems. We have already talked about few of the applications, like in opinion dynamics, we have the French tick root model, and we have also talked about wireless sensor nodes, and where multi-agent system, the tools from multi-agent systems can actually be used for time synchronization of wireless sensor nodes. And we'll be discussing a lot more ideas in more details in the 12th week. Yes, we will have more live sessions as well. Okay, so I'll now move on to the next student. Satish has asked a few questions. Could you give an intuitive meaning of algebraic connectivity in the context of agents working together? How does spectral graph, okay, very good question. How does the spectral graph influence the speed of consensus in multi-agent network? Are adjacency matrices just a mathematical tool, or do they have a direct interpretation? Okay. So let's start with algebraic connectivity in the context of agents working together. Okay. Now, what is algebraic connectivity? So we studied it in the context of the adjacency matrix. Suppose we have one network, or suppose, let's say, if you're perhaps an influencer who's trying to maximize his or her own influence, then what would you rather want to do? You would want to have more and more followers. What does a follower signify? It signifies that we now have an edge connecting the influencer and the follower. Meaning, if the influencer adds more and more edges, then its algebraic connectivity actually increases. Now suppose the next question actually answers the first question. It says that how can you give an intuitive meaning of algebra in the context of agents working together? Now suppose, and then the spectral gap of a graph influences speed of consensus. Yes. Okay. So I would like to write a few things. Or, okay. Either way, let me try to answer it. Or maybe let me join from another device where I can write. Okay, let me copy the Zoom link.
I can't hear you.
Am I audible now?
Yes, ma'am, you are audible.
So let's look at the Laplacian flow. We have the solution which this is our Laplacian flow. Under this, so the derivation of this I'll skip now, that's been covered in the lectures, but you only need to know that the solution of this takes the following form. So suppose we are assuming, let's say, an undirected graph here. V1 transpose x0 times V1 again, plus the second term is corresponds to the second eigenvalue of the Laplacian and the corresponding eigenvector. V2 transpose, so on, and the last term similarly is minus lambda nt Vn transpose x0 times, sorry, there's no transpose here, just Vn. Okay. So just to remind you, in the case of an undirected network, L is a symmetric matrix. Let us further assume that all of its entries are real valued. In that case, there are certain nice properties that the Laplacian has. What are they? First of all of the eigenvalues are take real entries for every I. And second is, we can always now arrange the eigenvalues in this manner, where the first eigenvalue, lambda 1, equals 0. And what happens to the rest of the eigenvalues? The rest of the eigenvalues are actually greater than 0 whenever the undirected graph is connected. Meaning, what happens in this case is, let's evaluate each of the terms individually now in the solution. So the first term is e raised to the power minus lambda t v1 transpose x0 times v1 again. So what is v1 transpose x0? If you remember in spectral decomposition, we want the eigenvectors to satisfy the normalization conditions, meaning we can now select when lambda 1 is equal to 0, a corresponding v1. If we use v1 equal to this, then it can satisfy both as the left and the right eigenvector. So this holds because the Laplacian here is a symmetric matrix. Now with this, let's try to analyze what we'll get. So the first term, e raised to the power minus lambda 1t, obviously becomes equal to 1. Then we have 1 by root n times all ones. And the initial condition is simply xn 0. And we have vn again. So v1 again, which is 1 by root 10 times 1n. If we now simplify this, what will we get? This is equal to, we can take this root n and root n common, and I can write it as 1 by n and 1n times x0. What is 1n times x0? It is nothing but the summation of all of the initial conditions, where I varies from 1 to n. And this entire thing gets multiplied with 1n. So what does this imply? It implies that, so let us say, let me denote this term as sum C, which is the average of the initial conditions, or it is directly equal to 1 by n, this summation. Then the first term here simply gives us a vector, all of whose entries are C. Let's go back to our solution. What did we see? We saw that the first term itself here in the solution leads to consensus. So what is the contribution of the rest of the terms? The rest of the terms are actually the terms of disagreement. Why? Because any addition to this causes disagreement in the system. Okay. What controls the rate at which the disagreement decays? Because see, every lambda 2 starting from here is greater than 0, meaning all of these terms are eventually decaying to 0. Every other term. And the rate at which they decay is governed by the spectral graph. So this is how algebraic connectivity matters. Okay, because the spectral gap can actually be governed, can actually dictate a lot of these properties, the rate at which the disagreement decays. Okay, I hope this has answered the question. Then the last part of the question is, are adjacency matrices just a mathematical tool, or do they also have a direct interpretation in real system design? Yes, they have a lot of interpretation in the real system design. The reason being that if you go over the lectures on Laplacian flows, or even simply the Laplacian, you'll realize that a lot of properties of electrical circuits can actually be, or depend on the Laplacian flows, can actually be defined using the Laplacian flows. Meaning, and the Laplacian flows are again related to the adjacency matrices. Meaning, in general, whenever we are trying to analyze real-world networks like an electrical circuit, adjacency matrices, Laplacian matrices do come up naturally. Meaning, they do have a role to play in a real system design, or when we are trying to design any system so that it reaches a desired behavior like consensus, or polarization, or clustering. I hope, Satish, I have answered your question. Okay, Leela has asked a few questions. In real-world applications like traffic networks or robotic swarms, How do network dynamical systems help us in understanding collective behaviors? Are there specific conditions under which individual agent behavior dominates over group dynamics? So, okay. Now, the answer to the first part of the question about applications in robotic swarms, we will look at some of these applications in the 11th and the 12th week of the course. So this question will get answered then. And the second is, are there specific conditions under which individual agent behavior dominates? Yes. Now, to make the question also a bit more specific, suppose we look at an application in opinion dynamics. So then we know simply by introducing stubbornness in agents, we can make sure that the opinions of some of the agents become much more important than the rest of the individuals. And sometimes having a suitable topology also helps. Like, let's say if we have a globally reachable node in the network, then we know that such nodes have more role to play than the other nodes in the network. Just to give you an example, again, we already have the setup of Laplacian flow written here. So if now we look at a network like this, now in this network, whenever we're using the Laplacian flows, eventually what happens is the states of all of the agents actually converge to the initial condition of the fourth node, meaning it is favored a bit more, not just a bit more, it is the only one who gets favored, and the others' initial opinions do not matter at all. So topology also plays a role in deciding which agents get favored and which do not. Now, Akashdeep also has some questions. And could you explain why eigenvalues and eigenvectors are important in analyzing multi-agent systems? Now, I hope the answer to this question is now clear from this. We see how the rate at which the agents converge to a certain desired state depends on the eigenvalues. Not only that, the stability of the system also depends on the eigenvalues. For example, if any of the eigenvalues here now became negative, what would happen? X of t would start growing arbitrarily with time, which is a very undesirable behavior. Hence, obviously, eigenvalues play a lot of role in not only the stability, but also deciding the rate at which we reach a desired behavior. And where do eigenvectors play a role? So again, this is something we discussed in the beginning of the lecture. Eigenvectors tell us the direction in which the solution ultimately aligns. So eigenvectors also play a role in dictating where exactly we are converging. The last question, please. In which state, what is the intuition? Okay. So in the topic of Laplacians, we have discussed how Laplacian matrices again appear quite naturally in electrical networks. So if you go over the lectures on the Laplacian, this question will be cleared. So these were all of the questions which were asked beforehand. Okay, there are a few questions in the chat box. So that who again is asked, are there? Okay, there are quite a few questions. Let's go one by one. Why is the spanning tree important in consensus? In the lecture, we only discussed global reachability. Again, a very good question. So why is it important? The idea is that now the communication between agents can be defined in two ways. What are those ways? First is if 1 and 2, let's say, if there is an edge from I to j, then either Aij entry can be greater than 0, or I can also have a convention where Aj entry becomes greater than 0. So whether the root node let me say it this way. Whatever is the role of the root node in, whatever is the role of the globally reachable node in this case, it converts to the root of a spanning tree when we reverse the direction of communication. That is why all of these notions are just a matter of how is the communication defined. So whatever we have read for global reachability can directly be converted. It becomes equivalent to the root of a spanning tree when we reverse the communication direction. Okay, Piyush has asked if there's a directed tree from the root, isn't every other node having exactly one path, so global reachability is still there? Yeah, that is why the concepts are actually equivalent. But we don't call it global reachability because so the only difference is that if this is my first graph and this is the other one, let me reverse the arrow directions here. And let me call it this node R. So here R serves as the root of the spanning tree, whereas if you look at this network, it is now a globally reachable node.
But the lecture only said that if there is global reachability, then there is consensus. But I think the root of the tree is not global reachability, right?
Yes, when we reverse the arrow direction, then we do not, then global reachability is not important anymore. We will look at the presence of the root of a spanning tree. So then we do not need a globally reachable node. We need this kind of a node.
And sometimes I read that's the condition of consensus of the graph, the spanning tree, right?
Yes.
But in your lecture, you just say the condition is global reachability, not spanning tree,
Yes.
right?
In
And I
the
don't
lecture,
understand nothing.
yes, okay. So in the lecture, we discussed global reachability because at the beginning of the lecture itself, we discussed that a communication is in this manner. Like if there's an arrow in this form, then J actually gives its information to I. However, if we reverse now the arrow direction, that J is giving information, I is giving information to J. In this kind of communication, global reachability becomes important. Root of a spanning tree becomes important. So both of these concepts are actually quite similar. It only is a matter of what is the direction of communication. And so how do we solve these problems? It is not important what is the direction of communication, but either way, whichever is the subgroup of nodes or the subgraph which is controlling, for example, let me modify this slightly. What is important here is, suppose this is a subgraph, which in our case is globally reachable. Suppose we reverse the arrow direction and we would want this to become the root of the spanning tree. Either way, this part has to be strongly connected when we are looking at the Laplacian flows, or it has to be primitive. The adjacency corresponding to this has to be primitive if we are looking at an averaging based model. That is the most important part, which actually decides whether or not consensus occurs.
I have one question. When I design the network to achieve the processor, we need to satisfy two conditions. The first condition is the spanning tree. The second is the global reachability. Right? Two conditions or one condition global. Can you explain for me?
Can you repeat the question? Or can you write it in the chat window?
Sorry, my background is so noise. And when we design a network to achieve the consensus condition, uh, do
Sorry,
we need to do we need to satisfy both conditions? The first
no,
the first
I
one is
the beginning. So when we are trying to design the network for what application?
yeah, uh, to consensus to achieve consensus. Design
Consent.
to achieve consensus. Yeah. And do we need to satisfy two conditions? The first one is global reachability. The second is the spanning tree. Do we need to both condition or one condition?
So both are not two different conditions. What I'm trying to emphasize is that both of them are actually equivalent to each other. It's just a matter of what is the convention? How are we representing the information flow? So we can actually drop all these, the direction of the edges, and rather think about it in this manner. Suppose there are a set of agents, perhaps a subset of agents, who are talking to one another. Let me mark this as some subgraph of nodes. So these subgraph of nodes form a strongly connected network, and they are aperiodic and all the nice properties that we want them to have. And these are actually disseminating their information to other nodes. Then this network, the overall network ultimately achieves consensus, and the value at which they achieve consensus depends only on the initial conditions of these set of nodes. Okay.
Thank you, thank you. I see, I see.
Okay. So then Mohit has asked, when do we care about consensus or limit at infinity or intermediate states? In this case, whatever lambda precisely. So the question is, when do we worry about the rate at which convergence happens? Valid question. In general, whenever we are looking at an asymptotic decay, what happens is anything that is asymptotic takes this form. Suppose this is how it decays. We see that obviously we must have heard what is a time constant. So why do we need to specify time constants? Because we know that the majority of the decay happens in that region. Now these notions can be specified by specifying, or they depend on what lambda 2 is. So while the decay is asymptotic, perhaps you want a better time constant. How can we achieve that? This can be achieved by controlling or choosing suitable values of lambda 2. Are there any cases where the dynamic equations described by Laplacian do not reach consensus, other than the graph being disconnected? So if you're looking at an undirected network, then for undirected network, if the graph is connected, then we always achieve consensus using Laplacian flows. However, if we now have a directed network, then even if the network is if the network is strongly connected, then the Laplacian flow will always lead to consensus. However, what can happen is we can now have, so here we showed only one network which is disseminating the information. Perhaps what could happen is we might have yet another network here, subgroup of agents. Again, they are strongly connected, aperiodic and everything, and they are also disseminating the information. So what happens is the rest of the agents in the network, some of them converge to the initial conditions of this, and the others will converge to this, and there will be others who will lie, whose opinions will lie as a linear combination of the opinions or the states of this group and states of this group. So all those things are possible when we have not globally reachable nodes, but are multiple sinks in the network. or not just sinks, but we actually have subgraphs. So basically, how do we specify these conditions? If we are to say it very precisely, then we will say when we draw the condensation graph of such a network, condensation graph, if the condensation graph has multiple sinks, then the system is driven towards disagreement. In dynamic graph, where connections change, very good question, okay? Would these metrics still remain important? Okay. So, okay. In dynamic graphs, where connections change, would these metrics? So, yes, of course, they play a role. Even in dynamic networks, we can talk about the rate at which convergence happens. So, how do we look at time-varying networks or in dynamic graphs? So while that is not covered in the course, I can give a basic idea of how it happens. Suppose we look at a network which is now changing with time. Let me mark some time instances here. I know that my network keeps on changing with time. However, what I observe is, let's say this is T, twice of T, 3T, and so on. So basically, T is some time period within which what I observe is the union of each of the graph in this region. If I take the union, then that union has all the nice properties that a static network would have, which is required for consensus. Meaning, the union of all these networks must now have a globally reachable node. Or if you're looking at the condensation graph, then rather a better way to say it is the condensation graph should have a globally reachable node. And when we look at the original network, the set of nodes which are forming the globally reachable node in the original network, they must be strongly connected and aperiodic. So basically, the union of all of the graphs must have nice properties of strongly connectedness and aperiodicity. So this is how we analyze time-varying networks. This is one of the ways in which we can do that. There are other ways as well. Okay. Please state the role of centrality measure when we design a network. When we design a network. So the centrality measure that we look at is completely dependent on the application. Meaning, any given network that we can have multiple kinds of centrality measures. But which centrality measure is relevant to us completely depends on the application. So if I may modify the question slightly, suppose we put it this way. Now, if we are interested in achieving consensus, however, we want a certain node to be central there, then can we design the network such that that particular node becomes central? The answer to that is yes, we can very well do that. For example, we've seen centrality measures like eigenvector centrality. So how does eigenvector centrality work? We know that any node which has a lot of important neighbors. And what are important neighbors? Again, those particular neighbors have a lot of friends. Or nodes, those particular neighbors have very high degrees. Then we know that this particular node is a very important node. Meaning now, if I want my node, which is, suppose it is, let's say my desired node. If I want my desired node to be the central node, what do? I add edges from this particular node to only the important nodes or to as many important nodes as is possible. Hence, I'm designing the network so that the particular desired node has very high eigenvector centrality. But again, eigenvector centrality is just one of the ways. There could be between centrality and closeness centrality. Again, for each case, we would have to design the network separately to have different or to have desired values of each of these centrality measures. Okay. If we have, the next question says, if we have a Fiedler value or some eigenvalue of graph or digraph, can we surgically remove certain okay, this is an interesting question. Can we surgically remove? So perhaps not a very technical term, but we can still, let me still try to answer this. Can we surgically remove certain eigenvalues or vectors from the graph? So the answer to this, the direct answer is maybe yes, but we do not know how. Meaning, suppose if we have been given a graph and we are trying to answer just by looking at the graph through some topological properties, can I exactly say what are all the eigenvalues and what are the corresponding eigenvectors? No, that is still an unsolved question. We cannot answer these things directly unless we are looking at very specific eigenvalues, which is, let's say, the second largest, which is the Fiedler eigenvalue, or even the largest eigenvalue, lambda n. In certain cases, we can also make comments on that. Now, the question is, can we surgically remove certain eigenvalues? So, no, the question is a bit ill-posed. Why? Let me answer that. Suppose we look at the Laplacian, its eigenvalues are L lambda 1, lambda 2, up to lambda n. This eigenvalue is equal to 0. This is my Fiedler eigenvalue. Suppose I surgically, somehow, I remove this, meaning, so I'm guessing the idea behind this question is that I'm deleting one of the nodes in the network. Say, these are all of the nodes in the network. I deleted just one of them, as hoping that this eigenvalue gets deleted. But no, we cannot directly say how to do that. And also, the Fiedler eigenvalue is not a property of one node alone. It is a property of, in general, how connected the network is. So it is not a local parameter, but rather a global one. And we cannot directly say, while we can say whether it will increase or decrease, we cannot take it to a very specific value just by deleting. Maybe if we do a lot of calculations, we can, but no, such topological results we do not really have. Okay, are there any other questions?
I have a question. Says the network classic described by dynamic equation with Laplacian. I see it's very light the Statsky equation. And can I plug in one input rule to control the state, the value of state of this equation? Can I do that?
Can you repeat the question?
Yeah, I have the I see the network that is described
Sorry,
by.
your voice.
Can you hear me? Can you hear me?
Your voice is breaking. While I can hear you, it is quite broken. Do you mind typing it? Perhaps then I can see the question and answer.
I will message. I will message for you. Wait for me.
Yes, we can absolutely use. Okay. Okay, this is also a very good question. So what is the most popular or common control technique that we use on linear systems? Let's say the state feedback. Now, when we are using the state feedback, in general, when we perceive the system to be a complete big system, or when we perceive it as a distributed system, what are the differences? Suppose this is perhaps, I don't know, any motor.
Sorry. And can I obtain the transfer function from the equation that is described by Laplace method? Can I do that?
Okay, again, your voice is breaking, so please feel free to type it out here. I'll answer all the questions.
Can you hear me? Can you hear me? Uh, can I obtain the transfer function from the dynamic equations that is described by Laplacian matrix?
I'm sorry, your voice is breaking and I'm unable
Okay,
to hear.
I will message. I will message.
Yes. So suppose this is some motor-based system, and this is a swarm of a flock of birds. What is the difference? Now, the difference is that in any kind of multi-agent based system, every node has a set of neighbors which it interacts with. Meaning, when I'm designing a control input, I must make sure that my input that is fed to this particular node is proportional or is a function of the states pertaining to only of my neighbors. Now, that is not a very trivial problem. While the Laplacian flow does ensure that, the averaging model does ensure, but if you're designing any system based on a standard control technique, then it might not ensure this property. What is the way to go around it? In that case, suppose if you use a state feedback controller or perhaps some other controller, which requires the information of state of some node which is not my neighbor, then I can always use a distributed observer. And that observer can perhaps give me the information of the state of this node. And then maybe I can use the control techniques. Okay. I can obtain a transfer function when going from the dynamic equation described by the Laplacian matrix, and when going to the transfer function, yes, you can do that, but please understand that the transfer function has certain limitations. It requires the initial conditions to be zero, and we did move to the state space model because of the advantages it has. And again, there are a lot of techniques. Of course, the control theory has advanced a lot, and we can use state space based approaches directly to design control techniques as well. Are there any other questions? Murthy, okay. In hub centrality, one is eigenvalue of A transpose, the other is A transpose A. Why does it give more information compared to just A? Very good question. The simplest answer would be now, the simple answer would be now in hubs and authority centrality, we are now actually not only we're trying to generate two rankings out of it. If we are using a standard metric like A, it does not tell us, it does not convey both the information. For example, if you're only looking at A, we perhaps can tell degree wise, which is the central node, if we just add up A. But here we are interested in both hubs and authority scores, meaning we are trying to figure out which nodes could actually be very good followers or very good sources of information for important or popular nodes. And these important or popular nodes are now the authority nodes. Since we have two different scores, now there is really no very easy way to get this information directly from A, but in this process, when we write A times A transpose or A transpose times A, then effectively we are able to separate out the role of authorities and the role of hubs. So that is how it actually gives more information compared to just using A. And the next question is, for exams, why do we need to focus on, do we need to focus on proof-based questions from the book or focus on numerical questions? So as of now, I would say, please focus on everything. Everything that is taught in the lectures is important, and whether it is important for the exam or not, it does not matter. It is important for your understanding. If we understand the proofs well, then it will help us in designing control techniques better. So please look at the proofs as well. Okay, that was asked. We can control the distributed system single link. System link, it means that we can control the distributed system like, I guess, a single agent system. In that case, yes, if we can use observers, then yes, effectively we can use the control techniques here as well. However, generally when we are looking at distributed systems, it is more intuitive if we can replicate the natural behaviors into a modeling process. So if we are relying on tools from graph theory or multi-agent systems, then it is slightly better, because then the control design that we have is a bit more realistic as to how we interact. For example, when people talk to each other, how does information spread? Now, to model those things, it is a bit more intuitive to rather focus on the agent-based systems derived out of the adjacency or lactation matrices. What is the interpretation of AA transpose, as A is about connectivity? That is a very good question, and I will leave it as an exercise motif for you to prove. So this is something, again, which we derived in the lectures. So please try to figure it out. How does AA transpose come up in the hubs and authority centrality? Okay. Are there any other questions? Analysis. Yes, there's a very good book on matrix analysis. You can refer to that. That is one of the best books on this. If there are no other questions, then Murali, if you could, we could perhaps end the session now.
Ma'am, I just checked on the YouTube. There are no queries. So if our participants who have joined on Zoom, if they do not have any questions, then we can wind up the session, ma'am.
Okay.
Yeah, thank you.
Are there any questions from the participants? Any other questions? Please feel free to ask any questions. So we conduct one more live session, but either way, if always feel free to meet.
Yeah. Also, they do have a provision to post the questions on the discussion forum. Students, we will plan one more session, and we will post an announcement related to that later on. And thank you very much, ma'am, for your valuable time. Thank you all the participants for joining in and making the session very interactive. So we are ending the session now. Thank you.
Oh, sorry. You can share the lecture. Lecture. Can you share lecture note? Lecture note.
So the lecture notes,
Yeah.
because we are writing it, we do not really have access to all the lecture notes. We won't be able to share it at this point. So some of them were written live on a different place, so we do not have access to all of the PDF copies of it. So we won't be able to share it live at this point. Share the PDF at this point.
Thank you, ma'am. I'm going to stop the streaming now. Thank you, participants.
Thank you.